Hello, can you hear
So
me?
may I? Yeah, I can hear. Can you hear me well?
Okay. Thank you, Fernando, for accept your invitation for this talk. How you can see here, there's few people in the Zoom because the Chinese are using this thing called co-share. It's a kind of YouTube video, so they don't need the Zoom.
Okay.
And then probably if you have no problem, it is not an issue for you, you can have this meeting record. There is okay?
Okay. Yeah. Sure. No
Okay,
problem.
thank you. So, how you can see here, we have two Brazilians in Lucas and Norton. Lucas Seller,
Hi,
I'm not sure
Lucas.
you know each other, and
Opa,
Norton Almeida.
hi.
Uh,
Hi,
so,
Norton.
it's online already in the co-share, so the students and the other postdocs is going to follow by that website, okay? So you can
Okay.
start when you want. It's up to
Okay.
you.
So let me share my screen here. Okay. Can you see the screen? I don't know how
Yes.
to make this in a full view, perhaps. So yeah, thanks for the invitation. It's a pleasure to present this recent work here, where essentially we discussed some possible applications for tiny crystal phases, specifically in metrology in sensors of AC fields. So I am from a university in Brazil, Universidade Federal Fluminense in Niterói, Rio de Janeiro. The moment I'm doing a sabbatical time here in Germany at the University of Mainz, and then I'll stay till the beginning of next year and back to Brazil. So this work, it's on archive, recent preprint. If anybody is interested on more details about this, either, of course, you can look for me. I'll be very happy to discuss, or just go directly for the link as well. So before, I mean, there are many people that have worked with tiny crystals. So I should thank actually for many different collaborations at this point. But specifically for these sensors, I need to thank for the collaboration with Ana Sampera from University Autónoma de Barcelona in Spain, and also for Rosario Fazio in ICDP in Trieste in Italy. So just as a brief outline of the presentation, I'll try first to discuss these two main concepts that is what are time crystal phases, essentially the definition of these phases and how they can appear in different models showing either a discrete time translation symmetry or a continuous time translation symmetry. And then I'll also try to review a bit of the basic ideas of metrology. That is going to be important. And in the later moment, of course, I mean, that's the main goal of this project here is to use these two concepts or to merge tiny crystals and metrology and use specifically Floquet tiny crystals as sensors for external alternating fields. Okay. So let me say, if anybody has any questions also, I'll be happy to answer during the presentation. There is no problem for me. So first, let me start about what are these time crystal phases. So the concept behind this phase is a very old concept. It comes from Landau's symmetry breaking ideas that we know that is one of the cornerstones of modern physics. Which states, I mean, at classifying different phases of matter based solely on the different symmetry breaking phenomena. So this cornerstone, it says that in equilibrium systems, we can see the spontaneous symmetry breaking phases appearing when the ground state or some low temperature states of the system, they essentially fail to be invariant over the symmetries of your system when we are in the thermodynamic limit. And this was a very famous and a very successful theory for decades, I would say. And we can say many different phases that lies along this phenomenology. For example, in ferromagnetic phases, we know that the underlying symmetries of the systems or the correlations or interactions among the spins, they are usually have some SU2, Z2 symmetry related to spin rotation of the spins. But we know that due to the correlations between the microscopic constituents, if you go for a very large ensemble or macroscopic systems, they can fail to be spin rotational, and then we see the domains of aligned spins appear in the system, and we have a breaking of the spin rotations and ferromagnetic phases. We can also discuss about spatial translation symmetries that leads to the generation of lattices in crystals, and I mean, there are a bunch of examples along these lines. We can say also about charge density waves that break the discrete spatial translation symmetries as well, superconductors, gauge symmetries, Lick crystals, and many others. And it was somehow interesting that among all of the different symmetries that one can break in a Hamiltonian, in a model, it was only recently that Wilczek posed this question: if is it also possible to break the time translation symmetry in a system, and then you have a phase that is characterized by this specific symmetry breaking. And this was somehow the main question about time crystal behavior. So Wilczek proposed this idea, but he also proposed a simple model that could show this phenomenology. I'm not going too much in details of this specific model because it's going to be clear, because it actually is not a time crystal phase, but the main idea is here in any case, and it's interesting to discuss. So he considered essentially a system that is a one-dimensional ring model. So it had this periodic condition, and you threaded these the systems of these particles to an external flux. And you can think that under certain conditions, due to this flux, your particles, they could generate a superconducting behavior or superconductor phases that would lead to some superconducting current in your ring particle model. And if you consider that these quasi-particles or these particles, they also have some attractive interactions, then it could be that they also can break the spatial symmetry and generate some small lumps of the particles, and these lumps would then have some persistent dynamics along your ring model. So if this really occurs in this type of system, you could think of some order parameter as some density at the position x at time t, and this system actually shows some long-range order correlations of the density order parameter, not only in space, where these particles are traveling in the ring, but also in time. So you have some type of a very specific signal for this correlation function that displays this long-range order in time and space, and therefore will be a case where your system is breaking the underlying time translation symmetry of the model and will be generating some time crystal behavior in the system. So of course, after the proposal of Wilczek, there are a lot of discussions about the real possibility of this phenomenology here, mainly by Blum, Lee, and Bolovic. And among their arguments, I mean, they are very plausible. One of them is that, so then in this case here, your lumps, they are rotating particles, accelerated particles, and at some point then they should radiate. And if they radiate, then you lose this persistent time dependence of your signal, and you lose the time crystal behavior. And indeed, I mean, some works later showed that the ansatz used by Wilczek in order to show this ground state behavior here was not the correct ground state. And if you go for the exact ground state of the ring particle model, you really lose this time periodicity or this long range ordering in time. So I've heard, okay, maybe it's from my computer. Just a second. I've heard a noise that was seemed that was a message from Zoom, but I think it was from my computer. Sorry. So all of this discussion actually ended in a famous no-go theorem by Watanabe and Yoshikawa in 2015 that showed that any systems in thermal equilibrium can never show this time crystalline behavior. At least they showed for short-range type of Hamiltonians. So in some sense, the discussion started in 2012 by Wilczek, and 2015 there was this no-go that from one side, I mean, it was saying that it's not possible to generate this phase, but from the optimistic side, and this was the direction that people really pushed for, it was just saying that we were looking at the different framework. We were looking for time crystals in thermal equilibrium, where actually we should look then for out of equilibrium to be out of this no-go theory. And when I say out of equilibrium, it could be either preparing your system not in the ground state of your system, but some excited state, not an eigenstate of the Hamiltonian, like a quench dynamics, or some different setups also as driven dynamics, where you impose some periodicity to your system and see how it responds to your periodicity. And indeed, it was in driven dynamics, specifically in Floquet dynamics, that are periodically driven systems, that the main achievements of tiny crystals were observed. So in this type of Floquet dynamics, what we have is that the Hamiltonian, it's driven, but instead it has some very specific discrete symmetry in time, such that the Hamiltonian goes back to itself after multiples of a fixed period. So in this case, then, in order for the system to show this type of time crystal behavior, and here I'm going to put explicit that this is a discrete time crystal behavior, because now it's breaking a discrete time translation symmetry of my Hamiltonian. There are essentially three main properties that it should satisfy. So there should exist some observable O, and a class of different initial states, such that if you look for the expectation value of this observable and these initial states during the dynamics, you observe that there is some periodic response to this Floquet dynamics, but of course that the periodic response should not have the same symmetry as the Hamiltonian. So this function ft after a single multiple of my periodicity, it should not be back to itself. It should have some different subharmonic response for my underlying time symmetry. A second property is the rigidity, in the sense that this function or the periodicity of this response here, it should be a main characteristic of the time crystal or of your phase of matter that's generating there. So the periodicity of this function here should be robust against perturbations or any fluctuations that you have in your system. And a third condition that is also very important is that this should be a many-body phase of matter and not just some single spins that are processing or having some non-interacting dynamics. So this type of phenomenology here of rigidities and this non-trivial time dependence function, they should appear or they should persist in time only when we are in the thermodynamic limit, in the sense that this phenomenology here comes from the collective behavior of all of my spins, and is really now a phase of matter and not just a few particles or few body phenomena. So a model that showed all of these nice properties was done by Nayak, Bauer, and Ellis in 2016, where they combined two main gradients, that is the Floquet dynamics, this periodicity, and some mechanisms to avoid thermalization in your system. Specifically, they used the many-body localization phases to support discrete time crystal. So in the Hamiltonian, in their models, they have these two terms. One is time independent, that's given by MBL, and the other one is a time independent that at every multiples of my period t, I apply this X operator that, as will become clear, the role is just to make a global flip on all of my spins. So they consider this one-dimensional chain of spins that are interacting between nearest neighbors, but we can also have some transverse and longitudinal external fields, disordered fields in this case. And the X operator is just a global spin magnetization along X that makes the global flip of my spins. So let me just mention also that Ji, H, and Hi, H zeta, and Hx here, they should be somehow disordered fields in a way to support a many-body localized Hamiltonian in this case here. So just to be clear, so then the dynamics of my system, it's given by this Floquet unitary operator that once you initialize the state in a specific configurations, after n times the period of my Floquet evolution is essentially acting with these two operators n times. So the first one makes an NPL type dynamics that we know that can avoid thermalization. It's just some dephasing among the spins. And the second part makes this kick that is given by the global X operator that makes the global flip of all of my spins. So just to be clear, I mean, if I have all of my spins in a specific initial configuration in a classical state or a separable state, the role of these operators here, specifically when phi is equal pi, but it could be slightly deviated from pi as well, is just making a product of sigma x over all of the spins. So it's just making this global flip of all of my spins. And what they observe in this specific model, it's very interesting that given some initial separable state, just like the one that I showed, if you look for the magnetization along x, y, and z of all of my spins, you see that while very fastly the magnetization along x and y directions, they thermalize. I mean, they just go to zero, resembling infinite temperature thermal state for my spins. You see that the magnetization along the zeta direction, that is the one that is somehow interacting in the MBL nearest neighbor model. It kind of survives for a long time. And moreover, it shows this period doubling magnetization. So in between the kicks, the X operator of my model, the spins are roughly up or roughly down, and they do not lose this coherence between their dynamics. And then you apply the kick, all of them go down, and then they follow again by the MBL dynamics. Just the phasing do not really lose coherence or do not thermalize, and you see somehow this persistent period doubling magnetization. And this is the important point, that it means that the state is coming back to itself, or the observable is coming back to itself only after 2 times the period of my Hamiltonian. So in this way, they are breaking the time periodicity of my Hamiltonian. And moreover, if you wait for long enough time, this period doubling here, they start to wash and they just go to zero. You lose the perfect period doubling dynamics. But if you increase the system size, and here is just showing, for example, the absolute value of this magnetization here, you see that you have this very stable plateau where all of the spins, they are collectively flipping up and down. Of course, you have a lifetime, a finite lifetime, but if you increase the number of spins, you have more subsystems to stabilize this period doubling response. And the lifetime here in this case, it diverges exponentially with the system size. So it means that, yeah.
So just to be clear, the global spin flip, this phase is randomic or not? It's just
So this, this is fixed. Okay, so in the simplest case where the phase is equal pi, it makes a perfect flip of all of my spins. But and this is an important point. But this we want that this is a phase of matter. It should be robust to any imperfections in the Hamiltonian. So if the phi is slightly deviated from pi, so you can think that it's pi plus epsilon, and epsilon is not so large, you still see the same type of phenomenology. Okay, it's not completely random. It should be close to pi.
And this behavior depend on how deep in the MBL phase they are or not?
Yeah, exactly. It depends both on how this phase is close to pi and how deep in the MBL phase you are. I mean, not how deep you are in the MBL phase, but if you are at least in the MBL phase. So it would depend how large is the disordered interactions between your spins and these external fields as well. So if it's large enough such that the time-independent model would be in the MBL phase, then you have the possibility to generate this type of behavior here.
Okay, thank you.
Okay, yeah, no, you're welcome. And then, then you see that if you go to very large system size, the lifetime of this period doubling dynamics tends to increase exponentially. And if we are then the macroscopic limit or the thermodynamic limit, this period doubling persists indefinitely in time, and we really have the time crystal behavior appearing, or the time crystal phasing supported by this type of model. So right after the proposal of these theoretical models, there was 2 experimental papers. Today, there are many others using different platforms as well. But just to show that, I mean, they were able to show the main characteristics of these phases using either trapped terbium ions or nitrogen vacancy defects in diamonds. And the idea, it was essentially looking for this type of Floquet dynamics and this type of protocols as well. So they just use now in 3 steps the Floquet dynamics. So every period you have H1 applying for some time, H2 for other time, and H3 for a different time. But the main gradients is somehow the same of the proposed by Chetanayak, that in one part you try to make the global spin rotations the best as possible to the pi phase. In the second time, you make this a many-body phase of matter, and then you introduce spin-spin interactions among your constituents. In the third part, you add disorder in a way to avoid thermalization or to improve the NBL phase of your spins. And looking for this type of behavior, you see, I mean, this is the period doubling dynamics of all of your spins, all of your ions. So you see that they decay, but this is because of thermal behavior. Some other experiments, they improve this type of behavior. But if you make a Fourier transform of this magnetization dynamics here, you see the period doubling appearing very, very robust, also against imperfections. Therefore, really generate this type of phases in a prethermal behavior in these centers. So let me just mention that this is not the only framework or the only type of discrete Floquet time crystals that can appear. You can also employ different mechanisms to support them. As for example, showed by Russoman, or you can also use the Floquet dynamics, but instead of MPL, you can use long-range interactions that also help to avoid or to prevent thermalization. And they showed, for example, using the Lipkin-Meshkov-Click model, that is infinite range interacting model, on top of this global kick, that is essentially the same kick that I discussed before. And this model here, it has a set of spins, but these spins now have all-to-all interactions between them. And they show that if you are low energy initial states, such that you have the Z2 symmetry breaking in the LMG model, so you have macroscopic magnetization or ferromagnetic states in the low energy spectrum of the Hamiltonian, you can show the same phenomenology of time crystals here as well. Or your states are flipping between all up and all down, or ferromagnetic up and ferromagnetic down in the same way. And this persistence is only in the thermodynamic limit. You can also generalize this for higher level period tripling, quadrupling, or n-tupling general models. And one idea was done by Federico Surassi, where instead of looking for spin operators or just 2-level systems, you can look for d-level systems and play somehow with the clock algebra, or you can think that these d-level systems can be interpreted as some ticks of a clock, and then the kick is just making the ticks, and you go back to itself when you make a round overall of your clock operators. So I'm not going to details, but just to show that many different mechanisms and models could also help to support these models. Each one has its own peculiarities, but these phases can appear in many different apparatus, and it's quite interesting. So yeah, so here in this case, they use again the Floquet, and then you can use either NBL along the clocks or some disordered along these D-level systems, or also long-range interactions, and you show the persistence of the time crystal also in this case. So far, I was talking just about the discrete time crystals, but this could also break continuous time translation symmetry. And this was done, for example, using for these boundary time crystals. but perhaps I'm going to skip a bit fast here because it's not the main point. It's just to show that, I mean, also in open system dynamics, you can show some time crystal behavior, where instead of looking for the full degrees of freedom of your system, you are interested only on a subsystem that is still macroscopic, and this still macroscopic system evolves like open system dynamics, and you could show the symmetry breaking also in this case. In this case, it's also interesting because, I mean, we are automatically out of the no-go theorem because we're not looking for equilibrium. It's really an intrinsically non-equilibrium model because it's a dissipative model. And more interesting, you can break not only a discrete, but you can also break a continuous time translation symmetry in this type of models. So just to be more specific, you can consider models that has some boundary Hamiltonian that describe these orange degrees of freedom, some bulk Hamiltonian that describes the blue degrees of freedom, and some bulk boundary interactions. That is how these two macroscopic degrees of freedom interacts among each other. And if you're interested on the dynamics only of the boundary, you can trace out the bulk degrees of freedom, and under certain assumptions, you are left with an effective dynamics for the boundary degrees of freedom. That is just the Lindbladian master equation. And we know that there are two different terms. The one is the coherent term, and the second one describes the effective interactions of the boundary to the bulk once you trace it out the bulk degrees of freedom that are given by these Lindblad jump operators. And a very simple model that shows this boundary time crystal is just thinking about the cooperative emission of n spins that are coupled to a single cavity mode that leads essentially to the effective dynamics given by coherent Hamiltonian, that is just a magnetization along the x direction for your spins. And due to this collective coupling to the cavity, you have this collective decay of all of my spins acting as the jump operator. And then if you look for this analysis of the system dynamics in this specific model, you see this persistence of the dynamics or the breaking of time translation symmetry occurring in the thermodynamic limit. So for example, if you look for the global magnetization of all of your spins as a function of time, you see that it shows some correlations or shows some periodic oscillations. But while for small system size, these periodic oscillations, they tend to die, similar to the MBL model. As you increase the number of spins, the cooperativity of all of your spin dynamics tends to increase as well, and the lifetime of these oscillations increases. And then if you go to the thermodynamic limit, you see these continuous periodic oscillations of all of your spins in the system. Moreover, it's robust to fluctuations and imperfections, so it's another form of time crystal, but now breaking a continuous time translation symmetry because there is no Floquet dynamics in my underlying model. Okay, so given that, I mean, just a brief recap of time crystal behaviors. I would like just to go a bit on metrology or the main ideas of metrology that essentially trying to estimate a physical quantity. So the goal here is that you have some electrical or magnetic fields, some frequency or some temperature, any abstract parameter that you want to measure. And then metrology try to obtain information about this quantity using a quantum sensor. So the basic steps is just you have your quantum sensor, and you have your quantity that you want to measure. You put the sensor in contact to this quantity that you want to measure, such that the evolution of the sensor is going to encode somehow the quantity that you want to measure. And then you measure your sensor in a later moment and try to extract this information that was encoded there. So just to be more clear, we can think of 4 basic steps for a metrological protocol. That first is the preparation of your sensor. You're preparing some useful quantum states that could be interesting for your protocol. In the second step, you put the sensor not in contact to this external field. and make the evolution. So then the external field that I want to measure is G, for example, and it's encoded in the unitary dynamics of my system. And then in a later moment, I make the measurements of my sensor that now somehow the information about G is encoded in its degrees of freedom. So I can make a POVM measurement, some different projectors, and obtain the probabilities of measuring the J projector at time t, given that G was the parameter that I want to estimate, that is just the trace of my density matrix to the POVM operator. So given that I do this many times, I obtain a set of probabilities, right? And then from the set of probabilities, I can use some approach for estimations or some likelihood or Bayesian estimation procedures to extract the G operator and the corresponding uncertainty of this G operator. So a very simple example, but that's going to be very useful very soon, is that imagine that you want to measure the amplitude of a magnetic field of a single spin, let me say. So then first step, you need to prepare your sensor. So given, let me say that your spin is initially up, I can prepare in such a way that they are going to be orthogonal to this external field that I want to measure. So I can prepare, just make a pi over 2 sigma y rotation of my spin and making it now to point along the x direction. In the second step, then I put the sensor or this initial state in contact to my Hg Hamiltonian in order for the G factor to be encoded in the dynamics of my sensor. So now if we do this, we know that the spin is going to process along this external magnetic field. And this G parameter is encoded now in a local phase of my spin sensor. Then in the third part, I want to make some measurements of my sensor. In this case here, a good measurement is just looking for the projectors along the up and the down direction. And if I do this, I mean, I can just rotate back to the initial configuration of my system. But if I do this, I obtain the probabilities for to obtain the spin up or the spin down. They are just going to depend on the sine or cosine of my parameter that I want to estimate versus time. So if we obtain then these probability distributions here, we know that the parameter that we want to measure is encoded there inside in some way, and then we can try to extract this using some different approach or estimation theory approach. You can think in the simplest case, you can just make a Fourier transform of the signal that you obtain here, and the frequency is what you want to measure. But of course, that you have some uncertainty also when you make the Fourier transformation, and then you have some uncertainty to this estimation protocol as well. So this is the main idea, but we also see one of the main obstacles in metrology is that if this signal that you want to measure, or this parameter G that you want to measure, is very, very small, then you see that in order to discriminate very small frequencies, you need to make a very long time protocol or large interrogation time for this to obtain better accuracy in this protocol here. And at the same time, if you need a large interrogation time, we know that usually our spins, they suffer from some environmental noise, some imperfections in the protocol, and we have just a short coherence time usually for my quantum systems or my quantum sensor. So this is one of the main obstacles in metrology, in the sense that we need to improve either the coherence time of my system or use some different mechanisms in order to probe infinitesimal external fields in metrological protocols. And moreover, I mean, you can think in the best possible way that you could perform, or in the best POVM measurement that you could apply in this metrological protocol. And there are some important bounds for the best precision that you can obtain for the estimated quantity, obtained by Olevo and Fisher and many others in the past years, that says that the minimum uncertainty of this estimated quantity is always bounded by 1 over the square root of these two quantities here, where m is simply the number of repeated measurements that you do, or the number that of times that repeat the protocol. So if you repeat this a lot of times, you increase your sample or probability distribution sample, and this helps you to estimate with better precision the external field. And the second quantity is the Fisher information that is going to be the main figure of merit in the next slides for the analysis of the metrological sensing. So the Fisher information is given just by the derivative of my wave function with respect to this external G field. And you can see somehow like the susceptibility of my quantum state to slight variations of this external field that you want to measure. So in some sense, you see that if this derivative state is very large, it means that small fluctuations or small variations of this external field tend to change abruptly the response that you obtain from it. And in this way, you can try to exploit this absolutely or instability of my state in order to improve or to extract the information of this field that's encoded inside there. So just going back, there are two important also bounds to the Fisher information, or to the best precision that you can obtain in a sensor. One is obtained that if you have a separable state, so now instead of a sensor of a single spin, you have n spins, but these n spins, they don't have any quantum correlations. They are just classical or classically correlated. Then in this case, the Fisher information has also a bound, and the bound is just the number of particles that you have and the t to the power of 2, the square of the time, or the square of the interrogation time that allows for your sensing protocols. So in some sense, it says that if you do not exploit quantum states, this is the best precision that you can obtain, that is just inversely proportional to t and to the square root of n, apart from the number of repeated measurements that you apply to your system. On the other side, and this is called the standard quantum limit. On the other side, if you now exploit quantum correlations or quantum sensors, as for example, you use entangled states as your sensor, the Fisher information now has a new bound, where instead of the linear scaling with the number of spins that you have now this quadratic scaling with the number of spins. And this is called the Heisenberg limit, and it somehow shows that using quantum correlations can boost the performance of my sensors in a nonlinear form, and this can be very useful for practical protocols as well. Okay, given that these two, let me say, a bit brief discussion about metrology and what is time crystal, the main point here is to discuss how can we merge these two concepts using then Floquet time crystals as sensors. So the idea, as it was somehow clear, is now that we have a system that is a many-body system that can act as our sensor, and we want to measure some external field using this many-body sensor in such a way that we can also profit from the entanglement enhancements of the many-body interactions in my sensor. So specifically, we are looking not for a constant magnetization, as in the example that I showed, but actually we have an external field that is a periodic signal, is an AC field. And the goal is to estimate the amplitude of this external field, so this HAC parameter here. So the full Hamiltonian of my spins is given then by the internal dynamics, H0 of my spins, plus these interactions to the external AC field that creates some magnetization along a specific direction of my sensor spins. So we have this cosine or sine function attached to a specific interaction term, and the sensors evolve locally with the internal Hamiltonian. So let me just say that when we look for AC sensings, it imposes also some further challenge, because now we are acting with a driving Hamiltonian in the system. And we know that driving Hamiltonian, a time-dependent field on my system, tends always to hit my system. I always acting with some force on some spins. And if you acting with some force, your spins tends to always absorb energy, heat up, and in the long time, it should just resemble a thermal state and lose any type of interest information that could encode there, as for example, the information of this external field. And this is one challenge that needs to be tackled. Usually there are different approaches in order to do AC sensing. The most famous comes using what is called the dynamical decoupling of my spins, where you, on top of this AC external field, you impose also some very fast pulses, some high frequency pulses to my spins, which can help to mitigate the decoherence or the heating of my system. So in some sense, you can mitigate one of the challenges of the sensor in this sense. But these dynamical decouplings, they also destroy or mitigate the interactions between the many body spins of my system. So in some sense, you improve the interrogation time because you have lower heating, but you cannot exploit anymore any entanglement enhancements because you also mitigate this type of interactions. So you can either prepare in purely separable states or using also these fast drives and preparing GHZ-like states in order to avoid the heat up. And these are the dynamical decoupling approach. But let me say that one of the inspirational work for this project here was this one by Bayat and Mishra, where they do not really go for this dynamical decoupling or fast pulses. They actually go for the non-equilibrium dynamics, but they look for some integrability of my system in order to mitigate the heating, but still trying to exploit the many body correlations of my spins. And this is essentially what we try also to exploit in this Floquet time crystal acting as the sensors. So in our sensor, we define as this internal Hamiltonian here, H0, exactly the same model that I presented in the first slides. That is the one by Chetanayak, Bella Bauer, and Dominic Els. That is this one-dimensional spins with disordered MBL Hamiltonian on top of some external kicks that make the global flip at the multiples of my period. And the external field is just the sinusoidal behavior here. So what's the physical picture then that we should expect in this type of sensing protocols? So we know that the spins of my sensor, they just follows a discrete time crystal behavior. So we have this period doubling dynamics of all of my spins. That is a collective response to my kicks. Then on top of this, they are also acted by this external AC field that may decohere or dephase the internal dynamics. But then if we try to put the internal period doubling dynamics in resonance to the external field, then we can try to preserve this collective behavior or this large coherence time in a good way for the sensing protocol. So the physical picture here is that if we try to put this period doubling resonance, this period doubling dynamics of my internal discrete time crystal spins in period doubling resonance to the external field in such a way that when this external field is positive, let me say that all of the spins, they are pointing along a single direction. But then the external field, they flip its sign, but we can also flip all of the spins because of the period doubling dynamics in such a way that they're always in phase now. Then we can extract or encode in the best possible form the external field into the internal dynamics of my sensor spins. And in fact, this is somehow what we obtain with some good performance for the sensor in this case. So just looking here, for example, first in the linear response that we want to measure infinitesimal fields, external fields. So we just look first for the limit where h is going to 0 or it's just infinitesimal linear response. And then first just remember the period doubling dynamics of the system that shows this type of plateau. And then after the plateau, the spin starts to the phase and you start to thermalize the systems up to 0, where resembles a completely thermal state. But the point is that the characteristics time here to thermalization is exponentially with the number of spins. And then if we study the Fisher formation or the performance of this sensor to these linear response fields, we see also 3 different characteristic time scales in the performance. So here, just notice that I'm showing the Fisher formation divided by nt square. That is the classical limit or the maximum that one can do with just classical correlations in the sensor. So we see that first, for a few time steps in the period, they are just essentially the same. That is just this first time steps of the period doubling. This is just a very fast relaxation, and then it starts to see the many body localization, the dephasing mechanism, and the real time crystal behavior. So the Fisher has some growth, but then once we enter in the completely stable period doubling dynamics, the Fisher reaches the standard quantum limit, and it stays there for this bound or this plateau here, and then it starts to grow again up to a maximum. And this growth here, it says that we can go beyond the classical limit, or we're really exploiting the quantum correlations of my spins for the sensing protocol. So we see essentially this corresponds to the period doubling dynamics and the Fisher information that can both saturate the classical bound and also overcome this classical bound, exploit the entanglement among the spins. And this can be actually seen a bit more quantitatively, where you can extract these time scales for the plateau time and the period doubling dynamics of the discrete time crystal and the Fisher information, and you see a completely agreement between them. So let me say this first line here is just the time, the lifetime of the plateau period doubling dynamics and the lifetime of the plateau Fisher information. And they are completely very similar to each other. They agree very well. And the second line here is the lifetime of half my period doubling dynamics. So if you look for the half lifetime of the plateau, that is somehow in this line here. And compared to the peak of the Fisher information, that is the time till we see quantum enhancements in the sensor. You see that they agree very well as well.
Fernando,
Yeah.
you're not comparing with if you use like just an entanglement state to do the same thing, right?
No, in this case, yeah, this is an important point also. So in this case here, I didn't say, but I'm just I'm initialize the system in a separable state, and I let the system to evolve and see how the quantum correlations can grow also among the spins and could be exploited as the sensor. So in these specific plots here, I'm not exploiting the initial preparation of an entangled system. Okay.
You're not comparing like your Floquet time crystal Fisher information with a total like an entanglement. If you use like entanglement state to do the measure, right? Then you should
No,
be
yeah.
in square.
Exactly. It should be n square here if you compare with a maximum untitled state, right? Yeah.
Just one question, like it's hard to talk about MBL with 6 spins too, right?
So you need to do exactly. It's hard to talk, but the scaling behaves very well. Let me say, if you
And
see
that's
the
just
scaling,
another question. Like in this case, you're using like the usual randomic MBL. What happens if you use like the Stark MBL? Simple.
okay, no, this is also interesting. Actually, I know some people that are looking to this direction right now. Instead of looking for the randomic, they just look for the Stark, and they see some qualitatively similar behavior to what I obtained here, because the mechanism is the same, right? So you're allowing a long interrogation time, and in this longer interrogation time, you still have a robust period W response. Okay, it's just the mechanism is different, but you still can use this long interrogation time for the collective response. So I would say that qualitatively, it's a very similar behavior that they obtain. Yeah, there of course there's some peculiarities because in this Stark, you don't have this exponential with n. Actually, I don't know. You have the exponential with n also. Yeah. So yeah, it
I
would be
think the
similar.
biggest issue with the Stark will be is not all initial states will be.
No, but there are different versions. I mean, I think
Yeah.
there were some more recent papers that even for different initial states, not specific ones, you could still see the Stark localization there in the discrete time behavior. I think that the first one it was just for a specific type of Stark, but there are some other as well, and you could play with different initial states. I'm not sure if it's for any initial state as it is in the many-body localized phase here, but at least for a large class, it would be possible. Okay. And let me also mention one thing that is interesting. I mean, here I'm comparing with mt squared because the initial state is a separable state in these specific plots here. But we also did for initial states that are entangled state, and you see qualitatively the same behavior, but then you need to compare not n here, but the initial entanglement of your system that could scale up to n to the power of 2. That is the Heisenberg limit.
By the way, Fernando,
yeah, so then you could also exploit the initial preparation of the system and obtain this plateau and some further enhancements as well. Okay.
Fernando, I don't see.
Yeah.
Can you hear me? Oh,
yes, I can hear. Yeah.
Sorry to interrupt. Just in this plot you explain, this quotient, this nt squared, is the standard limit. I mean, this should not be one for greater than one for gain because this. I expected that when this ratio is 1, there is equality between the, I know, nt squared is the standard for...
Yes, yeah. So maybe I can come back here.
Yeah.
So, okay, yeah. So nt squared is the maximum that you can do if you're only using separable states or classical states. Okay. Anything that is...
Yeah. When you divide by this, the equality is not 1.
Not necessarily 1, because you can have some prefactors here that depends on the state or the initial state that you are. So in other words, I mean, it's not that I'm reaching the nt square. I'm just reaching a constant times nt square. And this constant is just a prefactor that depends on the state itself. But the important is always to look for the scaling with time and the scaling with the number of particles, because the rest is just a prefactor that is going to be important. Of course, the prefactor is going to appear here, one of the square root of the prefactor. But practically, I think that the most important is how this is scaling as you have more and more spins and you need more and more time. Yeah. But that's true, yeah.
Okay. So that horizontal line is the bound. There is gain when you are above this horizontal line.
Exactly.
Okay.
So let me say this horizontal line here, it's when you're doing what a good classical or the best classical sensor are doing. So in some sense, you can say, okay, it's good, but it could be better.
Mhm.
And then at some point, it starts to go beyond the plateau or beyond the horizontal line. And then you're really performing quantumly or exploiting the quantum correlation of your system. And this cannot be done classically. And this is let me say, the boost or the improvement of the sensor. Okay.
Mhm. Thanks.
You're welcome. Yeah, so let me say, I should have put also here, I mean, these results for different initial preparations, but let me just briefly mention again that if you have initial entangled states, you should compare not F with nt squared, but F with the initial entanglement t squared. That could be scaling up to quadratically n, but you see qualitatively the same behavior. Because you still have the stabilization for any initial state that you are in the NBL phase or in the discrete NBL time crystal. Any initial state should be stable and should show the same period doubling resonance. Not sure if the Stark is the same, but I'm sure that they have some general initial classes that still show the Stark behavior there. Okay. Further questions?
Thank you.
Okay. Okay, if not, okay, so just to complement here, I mean, you can also see the von Neumann dynamics of the system or the entanglement dynamics of my spins. And here I'm just making the entanglement of half spins with the other half by partition in the middle of the chain. And you see that also the growth of correlations or the growth of the entanglement, they go in accordance with these characteristic time scales. So you see the plateau of the entanglement appearing here. Okay, the end is here should be the opposite, right? 10 to 4 and not 4 to 10. I'm sorry. So you see that for n equal 10, that is the blue one, you see this very large plateau where the system has no growth of correlations. And it's where the fission formation also shows the plateau. But then as the correlations or the entanglement starts to spread on the system again, due to the phasing of the NBL, the fission formation can capture this entanglement in a good form and improving the sensor performance. This is when you start to grow again the fissure dynamics. So everything here was just looking for the period dummy resonance. That is when the sensor performs in its optimal form. But of course, that we can look for off-resonance effects, or we can make a full scanning for the system frequency over the period doubling resonance. And what we see is also very interesting is that we see this response of the fissure formation for different time. Yeah.
Sorry, when you come back to the previous plot, look like if you use the ergodic phase, it'd be better if you use the same idea.
Not exactly.
Because like, if you say like what is the reason why the fissure information is growing is because of entanglement, and ergodic phase you have more entanglement in
yes, but there are two things, let me say. One is that not all of the entanglements, they can be useful for a fissure. So it's not that you have a highly entangled state, but let me say that the fissure information is going to be high. So there are different classes of entangled states that are good for the fissure. Some others cannot be so good. So this could be one point to take into account for ergodic dynamics in general. And the second point is that if you have an ergodic system, after a very short time, you lose the coherence of your system because you're fully thermalizing the spin degrees of freedom. And then the fissure may have some initial growth, but then after just a few periods, it starts to decay because you're losing now the encoded information because you're losing the coherence in your system. So you don't have a long interrogation time.
Yes.
Yeah.
So you can think like the middle term between ergodic, like around the critical region, will be better.
Perfect. This is one of the main ideas also in general, is to exploit the criticality that you have a long correlation length in order to use these correlations for the fissure formation. And I mean, if you go back to the very precise definition of the fissure, it's somehow this how the state changed to a slight variation of the external parameter, right? And then if you are close to the phase transition, you expect a large susceptibility of your quantum state. Therefore, a large value for the feature and a good precision. So usually you can also exploit the criticality or the phase transitions to boost even more the feature information for the sensor. Yeah, this is a good point indeed. I'm going to show in the next slides also a plot for the ergodic phase. Perhaps it's going to be more clear also. Okay, so this is just showing that, I mean, if you look for different frequencies, you see that there are some off-resonance effects here, that the feature is best at period doubling, but you see that this response of the feature comes also in a response in a structured form. It's not just a noisy response, and this comes because we are in a phase of matter, in a discrete time crystal that should be robust to any imperfections in the protocol. So even though we cannot reach this very large peak, we still have some good enhancement around the period doubling resonance. In some sense, that gives the sensor some robustness to the coherence or some noise that could appear also in the physical setting. And moreover, I mean, you see that this could also work as a dual role for the sensor. Because if you look for this response here, you can somehow characterize that you are in this phase or in this other phase. So the sensor could be good not only for sensing protocols, but to probe the phase of matter that you are. This could be a good perspective that we have been thinking as well. So just to contrast everything here to the ergodic sensor, because then it's going to be more clear also. If we are not in the discrete time crystal phase for the sensor, either because the disorder is not strong enough, or the kicking is too out of phase, I mean, some other perturbations that you can think. First, you don't see any period doubling magnetization. Actually, you can see for different system sizes that after just a few period kicks, your system fully thermalized to a thermal state, infinite temperature states, and there is no trace of initial state or the magnetization of your system. And is roughly independent on the number of particles that you are, if n is large enough. And if you look for the response of the fission formation for the ergodic sensor, you see this completely different behavior. First, there is no structure response here because there is no structure dynamics in my sensor. It's just an ergodic phase. And second, here I'm showing again f divided by the standard quantum limit, that's nt squared. And you see that it's always below the standard quantum limit. And as time goes by, it stays lower and lower, meaning that you're losing more and more the information about the AC field that you try to encode in your quantum system. So it's perhaps for very short times you could still exploit this thing, but if you need a long interrogation time in your apparatus, it's not going to be so good. Even though, just recalling that in these long times here, the state is fully entangled, but it's not a good entanglement. It's a thermal entanglement, if I can say in this way. That's not good for the fission. So I'm almost there. I'm sorry, I think that I passed a few minutes. But if you go beyond linear response, we have some new characteristic time scales that appear at the order of 1/h, where now for this time is here, larger than 1/h. It means that the AC field is so strong settled in the dynamics of your system that it does not really matter which phase you are anymore. So in this case here, for these times longer than this new characteristic time scales, you start to lose again the entanglement enhancements and recover just the standard quantum limit of nt squared. So it's just it will behave classically, and there is no good improvement for these longer times for the AC sensing. So just a brief summary then of the main ideas or the main results of this approach is that if you look for the uncertainty to estimate its external AC fields as a function of time or as a function of number of spins, we see very different behaviors depending on the phase of your sensor. So if you look for ergodic sensors or non-interacting sensors, you see that it can even decay fast for a few periods, but due to thermalization or to the fast heating of these systems, you start to lose the precision, and then you're always above the standard quantum limit till some characteristic time that recover then the standard quantum limit. That is when the sensor is very strong now the AC is very strong now on the sensor dynamics. On the other side, if you try to exploit discrete time crystals, you improve this coherence time. So you see this fast decay of the uncertainty with time for exponentially long time with the number of spins. And moreover, this is always faster than the standard quantum limit. It means that the uncertainty decays larger than 1/t, with beta larger than 1. So you can exploit also the quantum correlations of my spins. In summary, so we believe that this could be an interesting apparatus for metrological tasks, which offers some interesting advantages. Let me say, first one is the slow heating due to the MPL and time crystal behavior that leads to coherence interrogation time exponentially large in the number of spins. Moreover, this slow heating comes together with some useful correlations for the Fisher that can allow us to overcome the classical limit. And what is intrinsic also in all of the discussion is that this is a robust protocol because it comes from using a phase of matter as the sensor, and therefore should be robust to any imperfections or perturbations that you have in the system. So just to conclude, I just try to discuss a bit about what are time crystals, some applications to metrology. Let me pose that interesting perspectives is really looking for other types of time crystals and how they would behave as a sensor. So either you can look for these stark time crystals, higher end-to-pose time crystals, open continuous time crystals as well. Each one has its own peculiarities, and I believe that it could help in different directions for the sensor tasks as well. Okay. Another point that perhaps is also interesting is one thing that we are discussing is that how to enhance these correlations. And one idea is really looking for the criticality of this model. That could be very important. So given that, so let me just say that a small advertisement, I have some open master, PhD, and postdoc positions in my university in Niterói, in Brazil. It's a very nice environment. It's a very nice place as well, very beautiful. If anybody is interested, just get in contact direct with me. And given that, I thank you for your attention and sorry for the time.
Thank you, Fernando. I think I have some questions, but for sure, if you look at the Norton, probably they can start. And how I say, just check here the co-share. There's like around 30 students there, but they don't make questions anyway. So I feel sorry because as when I think about the students, I would like to watch a talk and be able to make questions, right? But then it's okay.
Yeah.
So
No,
yeah,
that's okay.
I feel like
That's
a little
okay.
bit uncomfortable. Yeah, the students they're watching and then can probably
No,
watch
but
again.
that's okay. That's
So
usual. So,
I
yeah.
think Norton is there if you want to start. Norton, Rogério, another Brazilian too, a postdoc in São Carlos, is here. Norton.
Oh, just to thank Fernando. Fernando, nice talk. Thank you very much. I learned many things in your talk, so thank you very much. I have no question, Neto.
I just a really simple question. You show the spin model. You say they have like this kind of time crystal with the dissipation. This looks so strange. The collective spin. They have a collection of spins. One mode dissipate a lot to have like the effective in the blood.
Yes.
Yeah, I really didn't understand because look like yes. This steady state should be not like the zero magnetization for this in the blood.
So perhaps I not perhaps I went too fast on this part here because I just cut a few slides. So let me just say this sigma x here or the sigma minus, these are collective operators. They act in all of my spins. Okay. So if you look for the non-equilibrium steady state, So then it's trivial in time, right? Because you have reached the thermalization. It's not really a thermal state, but you reach the stabilization of your system.
Oh, no. Okay. So just to be clear, the S max is still sigma z base and XS. There's another condition between the omega and the K, right?
Yes, exactly.
I was just looking at the Lindblad. For me, the Lindblad is go for zero. Like all this.
So this is a very nice model, I'll say, because it's very simple, but it shows a phase transition between two different macroscopic phases. And exactly, I mean, if you look for it, if kappa is larger than the coherent magnetization or the transverse field here, and then essentially the rate of decaying of my spins is larger, and then at the end of the day, all of the spins, they are just pointing down, essentially.
So you can see like is a kind of dissipative phase transition, but it's totally different for the super radiant phase transition, correct?
Exactly.
It's totally different.
Yeah.
It looks like a super radiant Lindblad, but I understand now it's a different phase.
Yeah. I would say that if you have just the sigma zeta in the coherent Hamiltonian, it's just a super radiant dynamics, and then you have just a super radiant phenomena there. But since these things do not really commute between each other, you can generate some non-trivial phenomena as well. I mean, I think that I have, just a second, I think that I have some slides after the things about this thing. Yeah, so exactly, I mean, so this is the same model, right? And if you look just for the non-equilibrium steady state, you see these two different phases as a function of the ratio of the coherent magnetization to the dissipative one. So if the dissipation is too large, you have a finite magnetization in the steady state. But if the dissipation is smaller than the coherent, the steady state has no magnetization at all. Even though you have some quantum correlation, some different properties there, but the steady state is somehow a highly mixed state with no
that's
further.
the one I was expecting. So that's
exactly.
The solution I was expecting.
But the point is that if you are in this part of the phase diagram here, and you have large enough spins, the lifetime or the time to reach this non-equilibrium steady state condition, it increases with the number of spins. So if you're in the thermodynamic limit, you never reach this type of properties here. So
you're saying that like you should do like the time limit will be on the post-Klimakov with these spins, right? You're going to use some bosons. You write these spins post-Klimakov. That's the solution. Yeah, you could use different approaches, I would say, because this is a collective model, because either Schringer or Haustein-Primakov or spin wave approximations. But they will show that the lifetime of dynamics depends on n, and it diverges in the macroscopic limit. So it means that you have some metastability states that we never thermalize if you have large enough spins. I think that I have perhaps some plots of this. So you can look, for example, just for the excitations of the Liouvillean, that gives you the lifetime of these dynamics. And what you can show is that in this time crystal phase, where omega is larger than kappa, you have actually gapless excitations. So 1 over the eigenvalue here is the lifetime, and then you really have the divergence of these things. Probably this is another your work, right? This is my work. This is from 2018, I guess. I can give the reference here. So, but this is a different platform because it's a completely open system. Yeah, so this is from this work here. Because now we are in an open system. It's good because we also can break the continuous time translation symmetry. We don't need any Floquet dynamics or Floquet driving to go out of the no-go theorem, essentially. It's an intrinsically out of equilibrium phenomena here. And we can still exploit the time crystal behavior. Thank you very much. No, thank you. So you're in German now, not in Italy anymore. No. Yeah, I was last 2 months, more or less. But now I'm back to Germany and stay till beginning of next year there. I keep here.
sorry.
Okay, thank you very much. So, if Norton, Lucas, I don't know if he's there. There's no questions, so I'm going to let you work, and then I'm going to get in contact. I want to read this. In fact, I'll be sincere. I got more interest by the last part of the dissipative phase
Dissipative one.
yeah. Really interesting. This thing too. I want to
Yeah,
check.
no, no. I was considering to discuss more about this, but since the sensor is for a discrete time crystal, I just skip the bit. But yeah,
I know there's people working with these time crystals in China. That like here in the university, there's many people trying, students interested in these things now. So I think for them it'll be really helpful. But
yeah,
anyway,
that's nice.
thank you.
Okay.
You
No,
hope
thank
to
you very much.
get in touch soon.
Thank you, Fernando.
yeah.
Boa estadia
Thank
aí
you.
na Alemanha.
Obrigado. Tchau, tchau. Obrigado,
Grande
pessoal.
abraço.
Bye,
Até
bye.
Tchau,
mais.
tchau.
Thank you all. Keep in touch then. Tchau, tchau.